power series. In this section, we're going to look at a particular type of series called a power series that is very useful in higher level mathematics courses. It's useful because certain types of power series can be used to represent other functions. And that can have some usefulness in analysis and in engineering fields. So first, a definition. A power series is a series of the form sigma n equals 0 to infinity of c sub n x sub n. And so that would be equal to c sub 0 plus c sub 1 times x plus c sub 2 x squared plus c sub 3 x cubed plus etc. Now notice that this is really a polynomial. All right, it's an infinite polynomial. It has an infinite number of terms, but it's really just a polynomial. X is a variable. The c sub n's are constants called the coefficients of the series. Now, a power series may converge for some values of x and diverge for other values of x. Notice in particular one thing. Our series starts at n equals 0. Okay, most of the series we've dealt with have started with the index starting at 1. A power series starts with the index at 0. So just something to be aware of. Now, one thing that we're going to be concerned about is determining where these power series converge. And so we're going to see an example of that in just a moment. So for example, for what values of x is this series convergent? And we have sigma n equals 0 to infinity of x to the n. This is a power series, and if we were to expand it, notice that the coefficients are all 1. And so this would just end up being, starting with n equals 0, we would have x to the 0, which we take to be 1, plus x to the first, plus x to the second, plus x to the third, plus x to the fourth, and so on. Now notice that this is actually a series we've seen before. This is a geometric series. It's a geometric series with r equal to x. We're just multiplying by x to get from term to term of the series. So, when will it converge? Well, we remember that a geometric series converges for absolute r less than 1. So therefore, our series, this power series, sigma x to the n, converges for absolute x less than 1. And it diverges elsewhere, right? It diverges for absolute x is greater than or equal to 1. Now, a little bit of terminology that we'll discuss in more detail a little bit later. We say that the radius of convergence for this series is r equals 1. The radius of convergence is 1. So, in a neighborhood, in a radius of 1 unit from, in this case, 0, this series will converge. The interval of convergence is from -1 to 1. So a radius of 1 from the origin means from -1 to 1. All right, let's consider another example here. For what values of x is this series convergent? And we have sigma n equals 1 to infinity of n to the n, x to the n. So this would be n to the n, well, notice that this one's starting at 1, because if we started at 0, we'd have 0 to the 0, which is an indeterminate form. So we're starting it at 1, so we'd have 1 to the 1, x to the first, and so that would be, what, x plus 2 to the second, x to the second, so that would be 4x squared, plus 3 to the third, x to the third, that would be 27x cubed. And let's just write out one more term here of the series, 4 to the fourth, x to the fourth, and 4 to the fourth is 256 x to the fourth, and we could keep on writing terms. Now, this one doesn't match any patterns that we're necessarily aware of, so what we'll do here is we'll use one of the tests we've learned about previously. And considering the terms here, I see that n to the n and x to the n, I'm thinking to use the root test. So applying the root test, I'll take the limit with n approaching infinity of the nth root of absolute n to the n, x to the n. And so then that would become the limit with n approaching infinity. Now n is a positive number. X is not necessarily positive. X can be positive or negative. All right, so this ends up giving us absolute, the nth root of n to the n and x to the n, this would give us absolute of nx. So that would be the limit with n approaching infinity. Well, as I said a moment ago, n is positive, so I can bring the n outside the absolute value. Now notice that as n approaches infinity, doesn't matter what x is, infinity times some, assuming it's not necessarily 0, infinity times any number besides 0, this limit is 0 if x equals 0 and is infinity elsewise. So what that tells us is, remember, from the root test, if the limit ends up being infinity, then it diverges, and if it ends up being less than 1, it converges. So it only converges in that one case. So sigma n equals 1 to infinity of n to the n, x to the n, converges only if x equals 0. The radius of convergence is 0, and the interval of convergence is a set containing just the number 0. So this series will only converge if x is exactly 0. Let's see one more example. So here's another series, sigma n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And again, we want to know for what values of x is the series convergent. I would suggest that you pause now and try this one out on your own. All right, I won't list any terms of this series like I've done for the previous exercises, but let's just go straight to determining where is the series convergent. So what I see is, I see a factorial here in terms of n, and I see this exponential in terms of n. So what I'm thinking is this would be a good place to use the ratio test. All right, so applying the ratio test, that would give me the limit with n approaching infinity, absolute value of a sub n plus 1 over a sub n. And so that would be the limit, n approaching infinity, a sub n, absolute, a sub n plus 1, that would be negative 1 to the n plus 1, x to the 2 times n plus 1 over 2 times n plus 1 plus 1 factorial over negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. All right, now those negative 1 to the powers under absolute, those will go away. Right, those will go away. Now, simplifying a little bit, this would then give me the limit with n approaching infinity. I would have x to the 2n plus 3, and I would have a 2n plus 1 factorial over x to the 2n plus 1, and I'd have a 2n plus 3 factorial in the denominator. And this should still be under absolute value. All right, I've just gotten rid of the negative 1s. I don't have to worry about that anymore due to the absolutes. All right, after simplifying this, let's see, I've got x to the 2n plus 3 in the numerator, x to the 2n plus 1 in the denominator. Limit n approaching infinity, absolute, I would have an x square in the numerator, right? Because 2n plus 3 minus 2n plus 1 just leaves a power of 2. And let's see, I've got a 2n plus 3 factorial. And so 2n plus 3 factorial, using our understanding of factorial, that would be 2n plus 1 factorial times 2n plus 2 times 2n plus 3. So using that, removing any common factors, I'll have a 2n plus 2 and a 2n plus 3 remaining in the denominator. And that's under absolute. Now n's positive. X squared is going to be positive, so I really don't need the absolutes anymore. So now I can just write this as limit n approaching infinity of x squared over 2n plus 2 times 2n plus 3. Now this limit, now let's look at this. Remember, we're adjusting n. As n becomes very large, x is a constant, right? The way we're thinking of it right now, under this limit, we're treating x as a constant. And in fact, if we want to, I could write this as x squared times the limit with n approaching infinity of 1 over 2n plus 1 times 2n plus, I'm sorry, that should be a 2n plus 2 times 2n plus 3. I can bring that x squared outside because the limit is with respect to n. And now as n approaches infinity, that would give me x squared times 0. Right? A 1 over infinity is 0. And so this is going to approach 0. And that's good for the ratio test, right? Because that's less than 1. So what that tells me is, since the ratio test, since taking that limit gives me a 0, what that tells me is sigma n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial converges for all x. And so we would say its radius of convergence is infinity, and its interval of convergence is negative infinity to infinity. And so this series will converge for all values of x. So that's a nice thing. That turns out to be a very useful thing to have happen in analysis. All right, let's now talk a little bit more about what we mean by the interval convergence and the radius of convergence. Let's give some proper definitions. All right, so a more formal definition of a power series is a series of the form sigma 0 to infinity c sub n times x minus a to the n. What we've done so far has been a power series centered at 0. We've been assuming that the a is 0, but it doesn't have to be. We can develop a power series centered at any value of a, and it's called a power series centered at a. And for any power series centered at a, there are only 3 possibilities concerning the convergence. 1, The series converges only when x equals a. We saw this in our second example. We saw this in the second example where the series only converged when x was 0. The series possibility 2. The series converges for all x. We saw this in our third example. Example 3, there is a positive number r such that the series converges if absolute x minus a is less than r and diverges if absolute x minus a is greater than r. And the number r is called the radius of convergence of the power series. And in this case, we're supposed to check the endpoints for convergence to determine the actual interval of convergence. We saw this in the first example, and I didn't check the endpoints in that case because it was based off of a series that we were already familiar with. But we'll see an example shortly where I will check the endpoints to verify the interval of convergence. Alright, so let's see an example. We're asked to find the radius and interval of convergence of the series sigma n equals 1 to infinity of x to the n over n times 3 to the n. Alright, so I see these exponentials. I'm thinking ratio test. Alright, so applying the ratio test, limit with n approaching infinity, and let's see absolute value. I would have x to the n plus 1 divided by n plus 1 times 3 to the n plus 1 divided by x to the n over n 3 to the n. Simplifying, this becomes the limit with n approaching infinity, absolute value. I'd have an x to the n plus 1. I'd have an n and a 3 to the n in the numerator. I'd have an x to the n in the denominator. I'd have an n plus 1 and a 3 to the n plus 1 in the denominator. Simplifying, this becomes the limit, still n approaching infinity. I'll keep the absolute value for now. And let's reduce some things. Let's see. I have one more factor of x in the numerator. I have one more factor of 3 in the denominator. And the n and the n plus 1 I can't do anything with. Alright, so now I can write this as, let's see, the n is positive, the 3 is positive, the n plus 1 is positive, so I can write this as the limit with n approaching infinity of absolute x times n over 3 times n plus 1. Now, I can take all of the constants, everything that's not dependent on n, I can take that outside the limit. So I can rewrite this as absolute x over 3 times the limit with n approaching infinity of n over n plus 1. Now, the limit as n approaches infinity of n over n plus 1, you could apply L'Hopital's rule here, or just some whatever understanding. This part, right, this whole thing right here, that'll go to 1. So this limit becomes absolute x over 3. Now, remembering the ratio test, I want this expression now. I want absolute x over 3 to be less than 1. Well, absolute x over multiplying through by 3, that means that absolute x is less than 3. And so there, in a sense, is my radius. I've got absolute x is less than a number. So therefore, the radius of convergence is 3. Now, I'm supposed to now test the endpoints for convergence. All right, so let's test x equals 3. if x equals 3, then I would have sigma n equals 1 to infinity. I'd have 3 to the n over n times 3 to the n, which is sigma n equals 1 to infinity. The 3 to the n's reduce, 1 over n. And this diverges, right? This is a harmonic series. However, if x is negative 3, I'd have sigma n equals 1 to infinity of negative 3 to the n over n times 3 to the n. Now that negative 3 to the n over 3 to the n, that's going to end up being negative 1 to the n. So that's sigma n equals 1 to infinity of negative 1 to the n over n. And, you know, it's starting with the wrong sign, but this is really just an alternating harmonic series. Which converges. So therefore, my interval of convergence includes negative 3 and excludes positive 3. And so this series will converge for all values of x from negative 3 included to positive 3 not included. One more example. Find the radius and interval of convergence for this series. Sigma 1 to infinity of n square x to the n over 2 times 4 times 6 times 8 times up through 2n. Wow. Let's see. How would we deal with this one? I mean, of course, now would be a good time to pause and maybe try this one out on your own. All right, so here's what I would notice. This denominator, we've not dealt with something like this before, but what I would see is that this denominator, let me go with a different color here. 2 is 2 times 1. 4 is 2 times 2. 6 is 2 times 3, 8 is 2 times 4, and so on, and then the last factor is 2 times n. And so notice we would have a whole bunch of 2's. We would have n 2's, and so that would be a 2 to the n, and then what's left over is 1 times 2 times 3 times 4 up through n, and that would be an n factorial. And so the a sub n is n squared x to the n over 2 to the n factorial. And so that might be a little bit easier to work with. So I'm going to use that form, and I'm going to apply again the ratio test. Since I've got some factorials, I've got a couple of exponentials, the ratio test seems reasonable. All right, so this would then give me the limit with n approaching infinity. And let's see, I would have absolute value of n plus 1 square x to the n plus 1 over 2 to the n plus 1, n plus 1 factorial over n square x to the n over 2 to the n factorial. All right, simplifying. I'd have an n plus 1 square x to the n plus 1, 2 to the n factorial in the numerator, n square x to the n, 2 to the n plus 1, n plus 1 factorial in the denominator. Simplifying by removing any common factors, I'd have the limit with n approaching infinity. I'll keep the absolute values for now. I can't do anything with the n plus 1 square over n square for now. X to the n plus 1 over x to the n, that would leave a factor of x in the numerator. 2 to the n over 2 to the n plus 1 would leave a 2 in the denominator. N factorial over n plus 1 factorial would leave an n plus 1 in the denominator. Notice that there's a common factor of n plus 1, so I can remove a factor of n plus 1. And so then this would give us the limit with n approaching infinity. I can bring the x, I can write this as absolute x over 2, and I'd have an n plus 1 over n squared. And so I can write this as absolute x over 2 times the limit with n approaching infinity of n plus 1 over n squared. And notice that as n approaches infinity, the n squared takes over n plus 1, and so this limit, right, this limit is equal to 0 for all x. So therefore, since that's less than 1, so sigma n squared x to the n over 2 to the n factorial from 1 to infinity has radius of convergence infinity and interval of convergence negative infinity to positive infinity. Right? This series will converge for all values of x. All right, that concludes the presentation for this section.